Hi, my name is John Krochmalny, and I have developed these visual tutorials to accompany any technical training format that might be delivered. In this presentation, we'll explore series electrical circuits, how they utilize electrical energy, and how to calculate electrical terms. In this presentation, there will be three learning outcomes. Number one, describe what series circuits are. Number two, calculate series electrical circuit properties. And then number three, measure the series electrical circuit properties. To review our understanding of simple electrical circuits, we start with our understanding that all circuits have a source of power. This power source provides for the difference in electrical pressure needed to initiate a flow of electricity. In simple electric circuits, there is only one load, which is the total resistance to the circuit. According to Ohm's law, the flow of electricity can be determined by dividing the applied pressure difference by the total resistance of the circuit. In this slide, we see the applied pressure dropped across the pump as 120 psi. This is the same pressure dropped across the R1 load. It is also 120 psi. In simple circuits, there is only one load, in this case represented by the R1 paddle wheel. In this slide, we see a flow rate measurement of 5 GPM existing between terminals L1 and 1. As in all circuits, whatever flow rate is measured at one location will be the same flow rate measured in other locations. In simple circuits, the voltage applied in a circuit is equal to the voltage dropped across the one load that the circuit contains. In this case, the applied voltage and the voltage dropped across the R1 load is the same, 120 volts AC. Remember, there needs to be a difference in pressure before any flow can be initiated. Finally, as in all types of circuits, Ohm's law can be applied to determine the other properties associated with electrical terms. Now let's start examining the electrical series type of circuit. In this slide, we see in the water circuit a 120 psi pressure differential existing across the pump. As mentioned before, this difference needs to be applied for flow to happen. With this applied pressure, we see two loads marked R1 and R2. Remember, the loads of any circuit convert one form of energy to another. In these cases, the paddle wheel loads convert fluid power into rotational mechanical torque. Each load offers its resistance to the flow. In this slide, we see two loads, R1 and R2, having 120 ohms of resistance offered to the flow. In series electrical circuits, the number of loads added to the circuit are added to determine the total resistance of the loads offered to the flow. In this case, we see a total resistance of 120 ohms plus 120 ohms, resulting in 240 ohms of total resistance. When applying Ohm's law, we can determine the flow of liquid to be calculated by taking the P for pressure divided by the R for total resistance. 120 psi divided by 240 ohms of resistance gives us a GPM of 0.5. This 0.5 GPM is found anywhere in the circuit it is being measured at. In this slide, we see the blue and the red pipes. The blue represents the suction side of the pump, and the red the discharge side. Measuring the pressure difference between L1 and N and terminals 3 and 7, we find a 120 psi pressure differential. Looking at the individual paddle wheels, we understand that there needs to be a pressure difference across the wheels before any flow can happen. This pressure difference across the load becomes the load pressure drop. The pressure drop across the R1 load causes the flow to pass through the paddle wheel, causing the wheel to rotate. The same is true for the R2 paddle wheel load. There needs to be a pressure drop across the R2 load for that paddle wheel to move. Notice that the pressure dropped across each load, when added together, will equal the applied pressure developed by the pump. Energy cannot be created nor destroyed, but can be converted from one form to another. So, with this understanding, if we can apply this principle to fluid power circuits, we can also apply these same principles to electrical circuits. A sample series electrical circuit is shown at the bottom right side of the slide. Any series circuit is where the flow comes out of one load and enters another. In this circuit shown, the flow coming from the R1 load goes into the R2 load. The series circuit attributes are found by applying the 5 laws associated with series electrical circuits and are listed on the left. Starting with the first law listed, RT equals R1 plus R2 plus R3 plus R4. How many loads are wired in series? With this first law applied to series electrical circuits, if we total the resistances of each load in series, we can determine the total series circuit resistance. In reference to the two loads in this circuit, R1 has a resistance of 120 ohms, and R2 has 120 ohms of resistance itself. Added together, the circuit's total resistance equals 240 ohms. The first law of series electrical circuits states that the resistance total equals the value of the first resistance plus the value of the second resistance plus the value of the third resistance, etc., etc. The more resistances that are wired in series, the more the total resistance is increased. The second law of series electrical circuits has to do with the amperage in the circuit when the source of power is applied. The formula to find the value of the amperage is based upon the Ohm's law formula. Amperage is equal to the applied voltage divided by the resistance total. In this slide, we see 120 volts being applied to two loads of 120 ohms each for a total resistance of 240 ohms. 120 volts divided by 240 ohms of total resistance equals 0.5 amps. The third law of series electrical circuits states that the voltage drop across each load is equal to the amperage found anywhere in that circuit multiplied times the resistance value of that particular load. Referencing the R1 load having 120 ohms of resistance, and multiplying this times 0.5 amps, which appears anywhere in the circuit, it equals 60 volts dropped across that load. Notice that with the R2 load having the same resistance value, it also has a voltage drop across it of 60 volts as well. Since we need a difference in pressure to initiate a flow, this voltage drop across each load is necessary for the amperage to pass through it. We can also measure this voltage drop by placing our meter across each load. In this slide, we see the 40 volts dropped across the R1 and R2 load. The fourth law of series electrical circuits state that if we add together the individual voltages dropped across each load, it will equal the value of the applied voltage. Voltage applied equals voltage drop 1 plus voltage drop 2 plus voltage drop 3 plus how many other loads are in the circuit. In this slide, 60 volts dropped across the R1 load added to the 60 volts dropped across the R2 load equals the applied voltage of 120 volts. The fifth law of series electrical circuits state that if we take the value of the applied voltage and subtract from it each particular voltage drop across the individual loads in series, the value of 0 would result. 0 equals voltage applied minus VDR1 minus VDR2 minus VDR3. VD standing for voltage drop. R1 is the identifier of that particular load. Please make a note of these 5 laws involving the series electrical circuit. This would assist you in determining the characteristics of the series electrical circuit. Law number 1 states that RT equals R1 plus R2 plus R3 plus R4. The more loads that are placed in a circuit, the more the total resistance of the series circuit increases. VDRN equals A times RN. The N in this case is going to be an indicator of the particular load. So therefore, the voltage dropped across each load is equal to the amperage appearing anywhere in the circuit multiplied by that particular load's resistance. VAPP equals VDR1 plus VDR2 plus VDR3 plus how many other loads that you have in the circuit. The applied voltage is equal to the sum of the individual voltage drops across each load wired in series. 0 equals VAPP minus VDR1 minus VDR2 minus VDR3. VD, the voltage drop, R1, that particular first load. If we take the voltage being applied to the series circuit and subtract from it all the voltage drops appearing across each load, the value of 0 will be measured. Now, let's apply these 5 laws of series electrical circuits to this particular circuit. In this example, we see 240 volts AC being applied to 2 loads wired in series circuit. The R1 load having 60 ohms of resistance and R2 having 100 ohms. Notice that in this circuit, it has 1.5 amps of current passing through it. As stated earlier in this presentation, series circuits have 5 laws to follow in determining the circuit's attributes. The first one, RT equals R1 plus R2 plus R3. The second law, the amps A equals VAPP divided by RT. The third states that VDRN equals A times RN. The fourth, VAPP equals VDR1 plus VDR2 plus VDR3. And then the fifth law, 0 equals VAPP minus VDR1 minus VDR2 minus VDR3. We'll look at the resistance total of this circuit first. RT equals R1 plus R2. Adding these 2 load resistances together, R1 equaling 60 ohms and R2 equaling 100 ohms of resistance, we get 160 total ohms of resistance. Now that we have a total series circuit resistance of 160 ohms, we can use Ohm's law to determine the circuit amperage using the second law of series circuits. 240 volts of applied voltage divided by the circuit's total resistance of 160 ohms gives us an amperage value of 1.5 amps. If the amperage calculated is 1.5 in this series electrical circuit, this same amperage value is present anywhere in the circuit, between L1 and the R1 load, between the R1 load and the R2 loads, and between the R2 load and the N terminal. In one of the formulas involving Ohm's law, we can determine voltage if the amperage is multiplied times resistance. Therefore, we use the third law of series electrical circuits. The voltage drop across the R1 load is equal to 1.5 amps of current found in the circuit and multiplied by the resistance value of the R1 load. In the R1 load, 1.5 amps multiplied by 60 ohms of resistance gives 90 volts dropped across that load. 1.5 amps multiplied by 100 ohms of resistance of the R2 load gives us a voltage drop across that load of 150 volts. We use the fourth law of series circuits to find the applied voltage of the circuit. The 90 volts dropped across load R1 added to the volts dropped across the R2 load of 150 volts equals the applied voltage of 240. The fifth law of series electrical circuits state that the applied voltage minus the sum of each voltage drop across the loads will equal 0. In this example, the 240 volts being applied to the circuit, subtracting the 90 volts across the R1 load and the 150 volts dropped across the R2 load does in fact equal 0. To sum up series electrical circuits, all series circuit properties are found using these 5 laws that are associated with these types of circuits. Electrical wattage is the measure of power being consumed in electrical circuits. In reference to series circuits, power is consumed by each particular load individually, and there is the power consumed by the entire series circuit. In this slide, we can see the WT or wattage of the circuit, and then we can also see the WN, the value of the wattage in each particular load. Notice that located at the right side of the graphic are the 3 formulas associated with finding watts consumed by any circuit. Let's determine the total wattage consumed by this series circuit. Looking at the first formula where total wattage is equal to the circuit amperage multiplied by the applied voltage. 1.5 amps multiplied by 240 volts applied equals 360 watts of power being consumed. Looking at the first load, we can use this same formula to determine the wattage consumed by this first load. 1.5 amps multiplied by the load's voltage drop of 90 equals 135 watts consumed by the first load. For the R2 load, we can determine its watts consumed by this same formula. 1.5 amps multiplied by the R2 voltage drop of 150 volts equals 225 watts consumed by the load. Whether determining total circuit or individual load wattages, any of the 3 formulas can be used. Watts equals amps multiplied times volts. Watts is equal to amps squared multiplied times resistance, and watts equals voltage squared divided by resistance. Any of these 3 formulas could work if 2 of the 3 terms are known. Finally, when it comes to wattage, the term used for power consumed in circuits, the greater the number of loads placed in series electrical circuits, the less power is available to the individual loads. Measuring series electrical circuits with multimeters are easily done. These measurements confirm calculated values when considering the 5 laws of electrical circuits. Considering the first law of electrical circuits in series, we see that the total circuit resistance is equal to the sum of each load resistance. RT equals R1 plus R2 plus R3, etc. Note that to measure resistance, the load has to be disconnected from its power source. The meter could be placed between terminals 1 and 2 to measure the series electrical circuit total resistance. The meter is also placed between terminals 1 and 3 to measure the resistance of the R1 load, and between 3 and 2 to measure the resistance of the R2 load. In referencing the second law of series electrical circuits, to measure amperage, the series electrical circuit is broken and the multimeter is placed in series with the loads. It is important to remember that whatever amperage is measured in one area of the circuit, it is going to be the same value as in other areas of the circuit. The third law of series electrical circuits determines the voltage dropped across each load. Remember, there needs to be a difference in pressure before any flow can happen. The multimeter is placed between terminals 1 and 3 to measure the voltage drop across the R1 load. We can also place the multimeter between terminals 3 and 2 to measure the voltage dropped across the R2 load. The fourth law of series electrical circuits states that the applied voltage of a series circuit is equal to the sum of the individual voltage drops. VAPP equals VDR1 plus VDR2 plus VDR3 plus VDR4, etc. We can determine the voltage being applied to the circuit by installing the meter between terminals 1 and 2 or between L1 and N. The fifth and last law of series electrical circuits state that the voltage being applied minus all of the individual voltage drops across each load is equal to 0. In this slide, the meter is measuring the applied voltage of 120 volts AC existing between L1 and neutral. Notice that in this slide, the multimeter is measuring the voltage between terminals 3 and N. This measured voltage will measure the voltage existing at that terminal number 3, or the voltage applied minus the voltage drop across the first load. Notice that in this slide, the multimeter is measuring the voltage between terminals 2 and N. This measured voltage will measure the voltage existing at terminal 2, or the applied voltage minus the first voltage drop across the first load, and then the second voltage drop across the second load. This measurement will read 0 voltage difference between these 2 points of terminal 2 and N.